Hello everyone, my name is Jun, and today I'll present our work, the RGB-based 6D pose estimation for textureless objects using multi-view optimization. And this work is a collaborate between U of T and Epson Canada. So the 6D object pose estimation is an important piece in many applications, like the augmented reality, autonomous driving, and the robotic bin picking. And the goal of this pose estimation is to estimate this 3D object's 3D translation and the 3D rotation in the scene. In our work, we assume the object CAD model is given. And traditionally, when the object has rich textures, the 6D pose can be solved by feature matching. However, when the objects are textureless, this approach will fail. And to handle the textureless objects, many people leverage this depth data or use it together with these RGB images to solve the pose estimation problem. However, for depth-based methods, because they heavily rely on the steps data quality, the pose estimation performance can significantly drop when giving this poor depth data. And therefore, in the past decade, the RGB-based approach have been considered as an alternative solution. But the problem for this approach is that the measurement is only from 2D. The final 6D pose generally has low accuracy. And to solve these problems, some recent work leverage these multiple viewpoints to improve the final performance. But there are still a lot of challenges remaining, like the appearance ambiguities and the rotation symmetries. And for the object pose, its direct estimation of the posterior is not straightforward. For the object translation, it's more obvious and can be approximated using a unimodal Gaussian. But for the rotation, because of the symmetry and perspective ambiguities, we have to use a more complicated model, like the Gaussian mixture, to represent it. And here's an overview of our approach. We use a neural network to estimate these per-frame measurements and integrate them into a two-step optimization scheme. We estimate this translation first, and this information will then provide the scale and position information for the rotational part. And to estimate this object translation, we first get this object 2D center at each viewpoint. And with the known camera poses, we can estimate this 3D translation from the object frame to the world frame. And we leverage this deep neural network to estimate this object mask and the 2D object center. And we then associate the multi-view object centers and using this Gaussian-Newton approach to estimate this translation. And the object translation can normally converge within only a few viewpoints. And for the rotational part, the literature solve it with different methods, like the template matching or classification-based approach. However, all these approaches are suffered from the scale and the location change. For example, for template matching-based approach, we need to generate the rotation templates from a view sphere at a certain distance. And in the runtime, the rotation can be correctly matched when the detected object has a similar scale. However, when there is a significant scale change, the estimated rotation can be totally wrong. And in our work, we take the advantage of the estimated object translation to handle this scale change problem. And specifically, we can compute this object size and its 2D location in the image using this estimated object translation. And in the runtime, we can crop this object ROI, and the cropped ROI should have this object position in the center and have the same size with the training data. And given this multi-view acquired measurements, we can estimate this object rotation by constructing this residual. And to handle the rotation symmetries, we updated this per-frame measurement with the object symmetry labels. And the updated measurement should correspond to the minimum loss with respect to the global object rotation. And because of this measurement ambiguities, we further leverage this Gaussian mixture model as a likelihood function and use this max mixture formulation to optimize this object rotation. And here are the results for the object rotation distribution. And we can see that when receiving more and more measurements, the weight for the correct component becomes higher and higher compared to this false hypothesis. And we evaluate our approach against the state of art on the RGB dataset. And we train the network only on the synthetic data. And here are the results using a real-sense camera. And we can see the results are pretty accurate, even only using these RGB images. And for the quantitative results, we can see our approach achieves a very high performance compared to this COSY pose, even when comparing with its RGBD version.